Okay, so now that we've done limits, we've done enough that we laid the ground so that now we can define derivatives of real valued functions. Um, the derivatives are related to the idea of a rate of change of a function with respect to its input, or to the closest linear approximation to a nonlinear function. Okay, so this is by far the biggest idea of the course. How fast is a function f changing at some value of its argument? Okay, now we already have this idea. If I have a monomial y equals mx plus b, its graph is a straight line, and m is called the slope or the gradient, and it is a measure of if you change x by delta x, then how does delta y change? Well, it changes at a rate m is equal to delta y over delta x. Okay. So we already have a rate of change for monomials. That's this gradient m. Okay. For other functions, though, things look a little bit different, and you don't have this constant rate of change as you do for a monomial. Um, some parts of the functions of value may be changing faster than it. So for some values of the input, the value of the output might be changing slower or faster than for other values of the input. Okay. So then we can consider an average rate of change. We have a function that's nonlinear, and its input is varying from a to b. And if we draw wherever the point a, f of a is, and then we draw a line from there, it's called a secant line, from there to the point b, f of b, right? And that gives you an average rate of the gradient of the slope, or the gradient of that secant line, is called an average rate of change for the function over the closed interval from a to b. Okay. Now, let's suppose that we're looking for an instantaneous rate of change. How would we do that? Well, we modify. So our average rate of change for f on closed AB, the average rate of change is delta f by delta x, which is f of b minus f of a over b minus a. And for the instantaneous rate of change, what we say is, all right, I want the instantaneous rate of change at x naught. So I'll take a point x, and then the average rate of change from x to x naught is, by my definition, f of x minus f of x naught over x minus x naught. And if I can make x get as close as possible to x naught without actually being x naught, and then that limit actually has some value, I call that the instantaneous rate of change at x naught. And we use these two notations here, df by dx at x equals x naught, or f prime at x naught. They both mean the same thing. This is the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. Okay, now equivalently, if we let our x be x naught plus h is the distance from x to x naught, then I could also write it this way. Df by dx at x equals x naught is equal to f prime at x naught. This is the limit as h goes to 0 of f of x naught plus h minus f of x naught over h. Okay? If this exists, right? The limits don't always exist. So it's possible that the derivative at some point, or the rate of change, instantaneous rate of change at some point x naught, does not in fact exist. Okay? So if I now want to think of the derivative as a new function, so I have a function f, and then I have a function f prime of x, which gives me, or df by dx, which gives me the rate of change of x at each x where f is differentiable, then I can, then by definition, this is df by dx at x, or f prime at x. This is equal to the limit as h goes to 0 of f of x plus h minus f of x over h, if this exists. Okay, so now let's consider what happens if f of x, let's say, is a constant function. It maps reals to reals, and f always returns the value c for any input. Okay, well, it seems to me that if it's a constant function, it means it isn't changing. So I would want the rate of change to be 0. Okay, so let's see. Well, I need f of x, which is equal to c. I need f of x plus h, which is equal to c. I can calculate the difference, which is 0. Now the difference quotient, f of x plus h minus f of x over h, then is equal to 0 over h, which is equal to 0. Then f prime of x equals the limit as h goes to 0 of the difference quotient, which is equal to the limit as h goes to 0 of 0, which equals 0. So the rate of change of a constant function is 0 at every point. Okay, let's cite the derivative of f. So f maps reals to reals, defined by f of x is equal to x. So the domain is the reals, the codomain is the reals, and the range is all of the reals. Let's calculate the derivative. F of x equals x, then f of x plus h equals x plus h. The difference, f of x plus h minus f of x, is equal to h. Now we calculate the difference quotient. Sorry, that should have been f of x plus h minus f of x over h. That will be h over h, which is 1. And now if we take the limit of the difference quotient as h goes to 0, that's the limit as h goes to 0 of 1, which is equal to 1. Okay. Let's calculate the derivative of x squared. Okay, so the function is f maps reals to reals, defined by f of x equals x squared. Okay, so f of x equals x squared. That means f of x plus h equals x plus h squared, which we expand as x squared plus 2xh plus h squared. Now the difference, f of x plus h minus f of x, equals 2xh plus h squared. You get the difference quotient by dividing that by h. So you get 2x plus h. So then the derivative is found by taking the limit of the difference quotient as h goes to 0, which is then twice x. Okay. So that's a few examples. We'll see more rules for calculating derivatives later, such that we don't always have to go back to doing the limit definition of derivative. The idea of derivative is also closely related to the idea of closest linear approximation. So supposing I have a function f, and then I define a monomial y. So y is equal to f of x naught plus f prime at x naught, x minus x naught. Now notice that if you put in x is equal to x naught, so y of x naught would equal f of x naught. So y agrees with the function f at x naught. Also, if I calculate the derivative, the rate of change of this monomial, it will be f prime of x naught. Okay, so this monomial y, which I'm calling the closest linear approximation to f at x naught, is constructed in such a way that the value of y at x naught agrees with f of x naught. And the derivative of y, the rate of change of y at x naught, is the same as the derivative of f at x naught. Okay. So if f is some complicated function, we can use y to give us an approximation to values of f of x when x is close to x naught. Okay, and the graph of the closest linear approximation is called the tangent line, and it goes through the point x naught f of x naught. So there's a simple one. Let's say f of x is equal to x squared. I want to find the function that is the closest linear approximation to f at x equals 1. So this is the monomial, which will have the same value at 1 as f of 1, and it will have the same derivative at 1 that f will have at 1. Okay, well, f of 1 equals 1 squared is equal to 1. F prime of x is equal to 2x. F prime of 1 is equal to 2. So we want the monomial, which takes the value 1 when x equals 1, and it has a gradient or a slope of 2. Okay, so the closest linear approximation is y of x equals f of 1 plus f prime of 1 at x minus 1. And that's equal to 1 plus twice x minus 1. Okay, and this is the equation of the tangent line to the graph of f at 1, 1. So now, if we can compare, we can say, what is f at, say, 1.1, and what is y at 1.1? So how well does the approximation y of 1.1 agree with, how close does that come to the actual value f of 1.1? Well, here it is. Y of 1.1 is 1.20, and the actual value, f of 1.1, is 1.21. So that's not too bad. Okay. In the next segment, we will go on to consider how we can we consider rules for um, derivatives so that we don't always have to go back to doing the limit definition of the derivative.